Okay, let's take a look at the last of the colligative properties of solution, and this is called osmotic pressure. And osmotic pressure is a property that results from a natural movement of solvent when we have two compartments that are separated by something called a semi-permeable membrane, which is basically like a sieve or a filter that only allows smaller particles, which is usually your water molecules to pass through, but doesn't allow something bigger to pass through, like a solute particle. This particular phenomenon, where water moves from one side to the other due to that concentration difference through that semi-permeable membrane, is what we call osmosis. And because of that movement of water, so if you imagine, let's say you have initially the two sides separated that way, but then the right side has a higher concentration of solute, so the water is able to move through these separator in the middle, which is our semi-permeable membrane, and eventually that side is going to have a higher level of liquid compared to the left side. Because of that difference in height, it generates a pressure from the right side to the left side. We can make that two sides equal again by exerting pressure on this side down, and that pressure that we would have exerted to make the two sides equal again is what we refer to as the osmotic pressure of that system. Okay, we can actually calculate the value of the osmotic pressure by just looking at the molarity of the solution times RT. R here is going to be your gas constant. It's going to have the value of the pressure volume constant, which is 0.0821 liter atmosphere per mole Kelvin. And then your T is just your Kelvin temperature. This is quite useful for dilute solutions, and a lot of times, as you'll see, like in the example we're about to do here, is used to determine the molar mass of non-volatile solids, particularly biological molecules. So things like proteins, nucleic acids, and molecules of that nature usually have really large molar masses. And so to calculate it, we would add a little bit of a sample and figure out what is the change in the osmotic pressure that we observe, and that allows us to actually calculate the molar mass. So let's take a look at this example of how we do it. Here we have a 50 milliliter sample of an aqueous solution, so that's water-based, right? It has 1.08 grams of something called human serum albumin, which is a protein, and we measure the osmotic pressure of that solution to be 5.85 millimeters of mercury at 298 Kelvin. The question is, what's the molar mass of these serum albumin? So I'm going to do the work on the right side as usual. My osmotic pressure has a symbol pi, and pi is equal to mRT. And we're trying to get molar mass. Molar mass, of course, is mass over the number of moles of a given substance. So we're going to have to get to that number. Now, we were given the mass already. It was 1.08 grams. So all we need to do is find the number of moles. What we want to think about is in that osmotic pressure equation, where number of moles might be found. Well, it's going to be in that molarity expression. So we're going to first solve for molarity here by taking the osmotic pressure divided by RT. And keep in mind that you want to convert this to ATM, so that's why I have that expression on the top, 5.85 divided by 760, because your gas constant is expressed in ATM, right? And that's the reason why we need to do that, to make sure that all the units cancel away. And then we have the temperature given in Kelvin, so that cancels as well. That gives us this value as the concentration. And then to get the number of moles, once we know the molarity, is just multiplying the volume, which is also given to us in the problem, times the concentration, giving us 1.573 times 10 to the minus 5 moles as the number of moles of the protein. And then the molar mass is just the mass that we're given divided by that number of moles. And as you can see, this is a pretty large number, 68,655 grams per mole. This is very typical, by the way, of proteins of all kinds, because on average, they have about 10,000 atoms. And so it's not necessarily a number that is out of the ordinary for biomolecule, okay? So the last part of our discussion on colligative property would focus on the colligative properties of electrolytes, which is fairly similar to the way we would calculate the colligative properties of the non-electrolytes, with one major difference. And that major difference is the number of particles that are generated. So remember that colligative properties depend on the concentration of the solute. Now, the difference between electrolytes and non-electrolytes is that if I have, let's say, 0.05 molal NaCl, well, when I put it in water, the NaCl will split apart to Na plus and Cl minus, which means that the 0.05 is actually 2 times 0.05. Right? So the number of particles is actually higher by double. This is in contrast to something like glucose, which is a polar compound, but it's a non-electrolyte. If I say I have 0.05 molal of glucose, all I have is 0.05 molal of glucose. It doesn't break apart, doesn't dissociate into ion. That means that when we're calculating the colligative properties of electrolytes, such as NaCl or some other ionic compound, we're going to need to use what we call a multiplying factor here to account for how many ions are actually generated. And so this multiplying factor has a symbol I, and it's called the Van Hoff factor. And what the Van Hoff factor is just what the number that you expect in the electrolyte solution divided by the expected value for the non-electrolyte. Now that bottom number is always 1 for the non-electrolyte because you don't expect non-electrolyte to split. So the I for non-electrolyte is 1. The top number is just whatever you expect for your ionic compounds. So for NaCl, for example, you expect 2 because it breaks apart into Na plus and Cl minus. This is how all the equations are changed as a result of the addition of that Van Hoff factor. So you see that now I'm just adding the I in front of all the equations that we learned for the 4 colligative properties, right? For the vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Here's the interesting thing though, that I told you earlier for sodium chloride is going to be 2. Actually not quite 2. So if we actually do experimental measurements of the colligative property, we find that for NaCl, the I is actually 1.9. So this light blue color is the theoretical I, and then the dark blue color is the actual experimental I, the observed I. And you can see for something like MgCl2, we expect it to be 3 because it's 1 Mg and 2 chloride. We actually see the I of 2.7. The question is, why is this happening? Why didn't we see something that is as we expect? Well, the reason is because there is a phenomenon called ion pairing that occurs in solution. And all that means is the following. When we have a solution of NaCl, for example, right? So here's our NaCl lattice originally. When we put water around it, remember that what we say is that this is what ends up happening. We have our negative, we have our positive, and they're then surrounded by a bunch of water particles, okay? And so if that's what's going on, we expect that for every NaCl, we're going to produce 1 Na and 1 Cl, which means 2 particles. That makes sense, but in reality, this is not what's happening. It turns out that majority of the ions do get split up, as I showed you on the right side there, but some of the ions are actually still stuck together, but they're surrounded by the water molecule, okay? So that means that if we just assume that everything splits up into 2, that's not quite right. So that assumption would be sort of like the upper limit of what you expect to happen. It turns out that some of them are actually still stuck together, so then it'll be a little less than 2, right? The number will be less than 2 in terms of the particles that are actually produced because of all of the ones that you see here, you see some of them split up completely, some of them are still paired up together, okay? And that's why those numbers that you see here are not exactly matching with the theoretical expectation. Now, I'm not expecting anybody to memorize what the actual observed I is compared to the theoretical I. When you do some kind of calculations with colligative property, you just use your theoretical I to make your calculation, okay? And let me actually apply that idea to this example, pretty straightforward example, which is what is the freezing point of aqueous 0.00145 molal MgCl2. So here on the right side, all we're going to do is just use the formula for delta TF, which is now added with the I. That's your Van Hoff factor, Kf times molality of the solute. Since we're dealing with MgCl2, the theoretical I is going to be 3, and that's the number we're going to use. We'll not have to remember the actual observed I for MgCl2. And so your delta TF will be 3 times the Kf. This Kf I just found from that table. Here I'm showing you on the left side here, the table that I showed you before in the section on the freezing point and boiling point changes. So that number for water is 1.86 degrees Celsius per molal, and then the molality itself is 0.00145. And so the delta TF is going to be 0.00809 degrees Celsius, and of course the TF is just going to be the normal freezing point, which is 0 Celsius, minus that number that we just calculated. And so your freezing point is negative 0.00809 degrees Celsius, okay? But the key here is to note that that number is 3 times larger than what you would have expected for a non-electrolyte, because if it's a non-electrolyte, this 3 would not be included here. It would just be this times the molality, okay?